we have now imported an image from the local folder we have, and the code is available here in our in my GitHub repo. So you could download it using this link, and the link is already there on Sage on my classroom minutes. So I start a new notebook, a new file based on SageMath 8.1. If you use CoCalc, it will be fine. So we import an image, then we declared and we call the image that I have here in the folder, which is G1. So basically you need to download this in your computer and open this notebook file using Sage. And maybe you will say, well, Basil, how we will open it? We don't know how to open it. So I will show you. You go back to the main screen of Sage, which is basically Jupyter Notebook, basically, and you do upload. Now, once you do upload, you find the resources that you want. So, for example, my example for you is here in this folder, and I want to work in SageMath in 10 minutes. I will open it here. It will come. So I will do upload. Now, once I upload it, it will be a Sage notebook. Once I click on it, I will be running, I will see all the code that I have done for you before. Now, you need to check that you can see that this is SageMath 8.1 as a kernel. Otherwise, from change kernel, you could identify whether this is Python 2, Python 3, or SageMath. Now, the first one, which is basically, as I said to you, this is a markdown cell just to write any text that you want. Maybe you just paste a question that I gave you in the assignment, and then you start to import things into Sage. So this is like my first image. I import it, and I have to import this first. Excellent, because I'm not in the same folder. He's right, I am wrong, so I will have to leave. So I should be here where all the images I have already in the folder. So now I import it, all good. Now I will create the first graph, and as I said, you declare an object and you say this is G1 equal graph. This is going to be an empty graph. So if you want to try things out at any step, guys, from my code, inside my code, you want to try new things, you could just say G1.show, what will happen? Now this will give you an empty graph. So once you say G1 empty, it's going to give you an empty graph if Sage understands that I have not declared it before. Now sometimes if you said to Sage like B equal graph of 5, this is going to create a graph with 5 vertices. So once you say B.show, it's going to have 5 edges for you, 5 vertices, sorry, but with no connection between them. So we have created our first graph, okay? We have tested, and now we want to do some more testing on it. Maybe we just say, well, about G1, just to print the adjacency matrix. So once you press tab, Sage will give you all the methods available. Now, I know there is a method called adjacency matrix. How I can get more information about it? As I said to you, shift from your keyboard, shift plus tab, it will give you more information about it. So you could read. If you are not happy, click on the plus sign and it will give you more examples. So all you need to do is basically to copy them. So I will copy, see? I will copy this example and I will write it here in a new cell. I just want to try it. So this is ggraphs.cube graph, and I will run it, and then I will do show, and I will see what this looks like. So this is to create a cube graph for me with 4-bit strings. Now, if I want to print the adjacency matrix of G, he said to me in the help, once I just run, that this function take some arguments if you want to do sparse or vertices, or you can just call it as it is and you run, and it will print the adjacency matrix for you. Same with incidency matrix, same with everything else we have learned before. So that was our first graph, and we declare it, and I show you in the previous example how you can do edge by edge, and this method is going to create multiple edges inside the constructor of the graph. So just to recap on this point, guys, you could create a graph object in SageMath using many methods. Whether you create them from empty graph and then you add edges one by one, or you add all the edges at once as a Python list, or you add multiple vertices all together and then you chain or you tail them and then you relabel them. Because Sage by default, it will create a graph object with zeros and fives, with numbers. If you want to call your vertices a specific name, you have to use a method called relabel. It's called g1.relabel. So you have to call this method, and you will say to this method, oh, I'm going to call 0 something. And this is what you could use. So that's the first graph. And I have also another graph that I want to represent, which is U1. Now, U1 is a circle. So you see that U1 is connected to U2, to U3, up to U7. How I create it? I create a graph, then I create another method. In purpose, I did this where I call the method of add edges. Because once you do this, you have to specify a list. And inside this list, you said, okay, U1 is connected to U2, and the label is E1. So this is the label, guys. The label is E1. So you give the edge, starting point, end point, and name. Then I call a method of g2.show, and I said edge labels equal true, so I could see the labels that I have defined. So you see, now this is my circular graph. All the edges has labels, and I managed to rename the vertices as well. Now, one of the major functions we were studying to test whether two graphs are isomorphic or not. Now, you might think Sage will give you a very accurate answer, but unfortunately, because as I said in the videos, guys, isomorphism is a very complex problem. So you have to do the checklist, and maybe you are right. So when you say G1 and G2 are isomorphic, 90% you are correct about it. Because really, if you want to study this problem further, you could spend a huge amount of time to prove whether two graphs are isomorphic or not. It's much easier to say they are not, but to proving and disproving isomorphism is the difficult one. So Sage have a method to prove whether G1 is isomorphic to G2, but accuracy is not that good. So I won't use it as a perfect standard, the answer that you get in Sage. The best thing you can do is to follow the checklist. You check the adjacency matrix of two graphs. You check the incidency, the adjacency of the mapped vertices between the two graphs. So if, for example, in our example here, U4 is mapped to U2, is U2 neighbored with U5, and U5 is mapped with a neighbor to U7 in the same other graph, and check for structure similarity or difference. And always look for one single difference. Maybe number of edges, number of vertices, to say they are not isomorphic. So in the exam, don't try to prove they are isomorphic. Try to disprove they are isomorphic until you find no reason to say they are not. Is it clear, guys? So we have two graphs now, and I define this function. And by the way, you could just call this method straight away without my fancy function, but I just use it because it's basically give me more feedback. I understand. So now I got the adjacency matrix of A and B. I just want to check if the adjacency metrics are equal, and they are not. Now using my function, I call this function, and I'll say, well, graph 1 and graph 2, which is in my case, are G1 and G2. Are they isomorphic? And the graph, they are not isomorphic. And by the way, look to them. So this is like the first graph. You have here, how many? You have 5 vertices, but in the above graph, we have as well 5 vertices. Now, how many edges? Why I count them? I could call Sage to count them for me. So let me just go back and just say, well, this is the new cell. G1 dot number of edges. How much number of edges? There are 8. G1 number of vertices. They are 5. Now what about G2? G2 number of edges are 5. And what about G2 number of vertices? They are 5. So look, the difference between G1 and G2 came where? Not in the number of vertices, the number of edges, which means we cannot maintain adjacency and non-adjacency between G1 and G2. And this is like a fundamental condition for isomorphism to exist between any two graphs. Okay, now I could also use my fancy functions. And by the way, in GitHub there is another notebook I published for the 255, which has more functions that you could find useful, and you could use basically for weakly connected, strongly connected, acute vertices. And I think those functions are going to help you in answering my assignment. So you could also use the code that I post in this. Let me just close this. Now about what I was doing. So we have a proof that those two graphs are not isomorphic, and we have defined a function to return basically adjacency matrix. And now I want to work with undirected graph, where direction is involved in the equation. And here you will see, every time I want to create undirected graph, I have to call diagraph. Because this will tell Sage that I'm going to give you a paired order of edges, where U1 is going to U4 is different when you say U1, U5. Because in this graph, U1 to U5 is not exist. So it won't be represented. So this is directed diagraph. And I will say, okay, add the edges, and I will put them in order. Normally with diagraph, you have to be careful. So make comments about every single edge you create. Why? Because you get confused a little bit. Now, how you will start representing it? Maybe you will say to yourself, okay, I will start with defining U1, and I will put all incoming and outgoing edges. But this is really bad idea, guys. You will mix up, you will make mistakes. So my advice is start in a clockwise. Okay? So U1, U2, U3. Okay? And just make one single rule for yourself, that I will model, or I will add only the outgoing edge. I'm not going to model the incoming edge. So if you see here in my code, I say D1, add edge U1 to U4. I said only I will care at each vertex about the outbound edge, about the outgoing direction, not the incoming, which is the degree plus, not the degree minus. Do you want me to repeat what I'm saying? So when you want to represent undirected graphs, start in clockwise, and in every single vertex, just add the edge for the outgoing direction, not the incoming. So for example, in U2, I only model U2 to U5. I won't say U4 to U2. Where I will do them? Once I reach vertex U4, I will do that U4 have a connection to U2. So just to keep myself without making mistakes and errors. That's why I just care about the outgoing edge, not the incoming. The outgoing edge is the one I model in this graph. Now, you could also, as I showed you before, sometimes it's very useful to draw in Sage the 3D. And why the 3D? Now look to this graph, okay? In a 3D. It looks fancy, and by the way, you could rotate it, as I showed you before, and you can change the colors, you could do lots of things. But why this is really important? Now, if you go down and we want to basically implement this graph. Again, this graph is a digraph. I make the same thing. For example, in V1, I just make an edge for V1, V2, V1, V6. I ignore that there is an edge from V4 to V1 because I will do it here when I reach vertex 4. That's the point, so you don't make mistakes. Now, once you represent this diagraph, okay, and you run it, and you basically look to it as a 3D. So this is my second graph, and I think I have the first graph as well there. Wait a second. And if you look now to both graphs, what do you think, guys? Are they isomorphic or not in a 3D? They are like 100% isomorphic. So the reason why I teach you how to do the 3D, because the 3D help you to identify isomorphism. Because it will draw the graph in very similar way, so you could simply see in a 3D dimension whether they are isomorphic or not. So if you have a question in the book, in the assignments, in one of the activities I post, and you are not sure whether two graphs are isomorphic, come to Sage, draw them, and then show them in a 3D, and you will be very sure whether they are or not. All right, so the adjacency matrix, you look to it like this. You build a two-dimensional matrix, and you say U1 as the columns, rows U1. So you make rows of U1, U2, U3, U4, U5, U6. These are going to be the columns. And then the row is going to be U1, U2, U3, U4, U5, U6. And then at each cell between U1 and U1, ask yourself this question. Is there any edge between U1 and U2? Even in this graph. So you put 0. Is there any connection between U1 and U2? No, so you put what? You put 0. Is there any connection between U1 and U3? No. U1 and U6? No. U1 and U5? No. U1 and U4? Yes. If you are modeling now the outgoing, which is the plus degree, the plus sign, not the incoming and outgoing. Now, if it's assembly graph, okay, like this one, if it is assembly graph, when you model U4 as a column, in the row of U4, you just put 1 under U5 and U3. Now this is the adjacency matrix. It's U1, U2, U3, U4, U5. Now, is there any link between U1 and U1? Is there any loop? No. But is there any link between U1 and U2? Yes. So we put 1. Is there any link between U1 and U3? No. So we put 0. Is there any link between U1 and U4? Yes. So we will put 1. Is there any link between U1 and U5? Yes. So we put 1. Now what is the degree of U1? Is it 3. Now go back to the row in the adjacency matrix. You find the degree or the total numbers, the total ones in the row equals to 3. And same, for example, take another example like U3. Now this is 1, 2, 3, 4. So this is a 3. U3 is connected, it's not connected to U1, so this is 0. It's connected to U2, so this is 1. It's not connected to itself, there is no self loop, so this is going to be 0. U3 is connected to U4, and it is also connected to only U4 and U2. U4 and U2. So we have here 1 and 1. So the benefit of the 3D is to show you basically isomorphism. And as I said, guys, in the first class and in the videos, Sage is like, I'm not teaching you Python programming. My course is a graph theory. I use Sage as a tool for you to understand the theory. Really, like the point of using Sage is not to enhance your programming skills, rather than understanding the theory, because you will understand graph theory better with Sage. If you find Sage hard, you can ignore it. You can totally ignore it. There will be no code required about Sage in the exam. So I'm not going to ask you to write a Sage code in the exam. The point or the learning outcome and the learning objective of this module is the graph theory itself. So if you find Sage hard, ignore it. I don't want you to spend too much time if you stuck with Sage so you don't understand the theory. And this is, by the way, apply for the guys in 255 as well. This part, I show you how to use Sage and how basically you can employ Sage for your own benefit to understand graph theory. Now, and how to answer for the assignment. At any stage, you just use the hash key, the hash sign to make a comment. And this will be whether a headline with double hash or a normal Python comment where you can just say, this is question 1 answer. Now you want to submit it. It's time for you to submit the assignment. So what you need to do, from file, download as, you download it as a notebook file. So once you download it, it will come to your computer as this, SageMath in 10 minutes notebook file. And this notebook file, the one you need to submit for myself. So this is the one you upload to the cloud. You don't need to submit a Word file. You don't need to save those images as PNG and then make one single Word document or a PDF document. You don't need to do all of that. Just submit a notebook file. If you don't submit notebook file, it's going to be a problem because I have to see the code. Now, I don't advise you to submit a Python file unless you are depressed. You don't know what to do. Okay? Don't do PDF. I still accept PDF submission because once you do the PDF, sometimes it's not working. You have to have PDF server. You have to have a configuration. If you are using a virtual machine, it's not going to work. So my advice is to do file download as notebook file. Okay? So that's what we need to do about the assignment. So let us take another example. So the question is, in this graph, is basically, can someone cross all the bridges shown in the map exactly once and return to the starting point? What do you think, guys? Is it possible? No. Can you start at V2 and come back to V2, but you need to cross all the bridges in this map once and return to the starting point? Can you? Now go from V2 to V1, okay? Walk from V2 to V1. So V2, V3 are basically the island inside that between the two rivers, okay? Those are the two rivers, and these are the river, what they call, bank? Yeah. The bank V1, V4, and these are the middle land between the rivers. So I will start at V2. I go to V1, then I take a walk, I come back to V4, then I take a back to V3, and then I come back to V2, and then from V2 I go back to V4 again, and then I walk up to here and come back to V2. So there is nothing bad about that, right? Represent this graph. As I said, you can say those are the land in the middle, those are the bank of the river, so we have the following vertices, and our graph will look like this. We represent this graph, and now we ask Sage, what the number of edges? What the number of vertices? Whether this graph has an Euler circuit or not. Whether this graph has an Euler circuit, and the circuit is V1, V4, V4, V2, V2, and so on. Now, sometimes you need to use and to test whether you have Hamilton. And this is like the subject of this week. So you could ask Sage to use its Hamilton function and also to give you a Hamilton cycle. And Sage is really perfect in doing that. It could give you an accurate Hamilton representation. Now, if you want to use Hamilton path in Sage, you have to first make multi-edges equal to false, and then call the Hamilton path function in Sage, because this is designed for simple graph, not for multi-end diagrams. So this is like the Hamilton path. My last thing for today, I have also this method for you, which is basically a fancy for visualization things, where you can define a graph plot, and now you define a title, a vertex size, which is really big, so it fits the words that I want to include. I could also specify the edge thickness, the color of the edges, and also the size and color of the vertices. And I want to show the labels, and I want to label the graph, which is basically defined in here. So this is like my graph 2. I define it here, and I run it here. So you end up with this fancy, nice representation of the graph. Two things: whether you specify the color, red, black, whatever you want, or you specify HTML code color.